Okay, so now we're going to continue with our lecture on Chapter 5 with sampling distributions. First of all, we're going to look at sampling distribution of sample means. What we're going to be doing is taking many samples, all of the same size n, and we're going to be calculating their sample means. That's known as the sampling distribution of sample means. So for example, suppose I have a population which consists only of these 3 points, 1, 4, and 7. Now the mean of these, 1 plus 4 plus 7 divided by 3 is 4. And if we put those three numbers into Minitab and asked for the standard deviation, we would see it was about 2.45. Next, we're going to consider all possible samples with replacement of size 2. Okay, so we're going to consider this. We have these three numbers on 3 different pieces of paper. We're going to draw out one of the pieces of paper, record the number, then put it back. That's what with replacement means. Put it back in and draw again. So let's look at all the possible samples of size 2. We could draw out the number 1, but since we're putting it back in, we could draw it out again. Now let's calculate the mean of this sample. 1 plus 1 divided by 2 is 1. We could draw out a 1 and then possibly a 4. 1 plus 4 divided by 2 is 2.5. We could draw out a 1 and then a 7 and find its mean. 1 plus 7 divided by 2 is 4. Now we could also draw out the 4 first and then the 1, which is different than the 1 first and then the 4. But we would get the same mean. 4 plus 1 divided by 2 is 2.5. And we see that there are 9 possible samples of size 2 from these 3 data values and their respective means. So now we're going to be considering the mean values here. Notice each sample has the same probability of being chosen. Excuse me. Now, if we average all those sample means, we add up all those sample means, divide by 9, because there was 9 of them, we would get 4, which turns out to be the exact same number as the population mean. And if we put those 9 sample means into Minitab and find the standard deviation, we would see it is approximately equal to the square root of 3. Now notice, the sample standard deviation was 2.45. If we take 2.45 and divide by the square root of the sample size, which was 2, we would see this is equivalent to about the square root of 3. Now, sampling variability. If we take a bunch of samples and find the mean of each of these samples, each of these sample means is going to be slightly different. This is known as sampling variability. The next sampling distribution we're going to look at is the sampling distribution of proportions. Now, the sampling distribution of proportions is we're going to take all samples having the same size. Now, recall our example from before. We had the 1, 4, and the 7, and we're going to be, remember the mean was 4 and the standard deviation is about 2.45. We're again going to consider all possible samples with replacement of size 2. And this time what we're going to be considering is the proportion of even numbers. Now in our population we have 3 numbers. And of these 3 numbers, exactly one of them is even, the 4. So the population proportion is 1 out of 3. Now let's look at each of these samples of size 2. Now we pull out the 1 and then the 1. That was one of our possible samples. But neither number is even. So the proportion of even numbers is 0. Now here we again, one of our possible samples was the 1 and then the 4. Now one of these 2 numbers is even, the 4 is, right? So the proportion is 1 out of 2 is even. We continue doing this for all 9 possible samples and we see that we have these 9 proportions. Now, if we average the proportions, we saw that we had a proportion of a half. We had 4 proportions of a half, 1 out of 2. So 1/2 plus 1/2 plus 1/2 plus 1/2 plus the 1, the sample 4 was 2 out of 2. We saw that that adds up to 3 out of 9, or 1/3. That turns out to be the average proportion from our population. So let's look at the properties of the distribution of sample proportions. Sample proportion tends to target the value of the population proportion. And under certain circumstances, the distribution of sample proportions will approximate a normal distribution. Now, samples that target population parameters are mean, variance, and proportion. But which ones estimate their parameters poorly? Well, if they do that, if they estimate the parameter poorly, then they're known as biased estimators. Standard deviation is a biased estimator, so is the median, and so is the range. But as long as the sample size is large enough, then the sample standard deviations are close enough to the population standard deviation that we can use it as a good estimate, as long as our our samples are large enough. The central limit theorem is a very important concept in statistics, and it holds for sampling distributions of sample means. And we need to have these two conditions hold. First, the random variable x has a distribution which may or may not be normal, but it does have a mean, mu, and a standard deviation, sigma. And all of the sample sizes have to be the same size, and each sample has to have an equal chance of being selected. If that holds, then the conclusions of the central limit theorem is the distribution of sample means will, as sample sizes increase, approach the normal distribution. The mean of all the sample means is equivalent to the population mean. We saw that with our example a little bit ago. And the standard deviation of the sample means turns out it is always going to be equal to the population standard deviation divided by the square root of the sample size. And here are two practical rules that are commonly used. If the original population is not normally distributed, but the sample size is large enough, and large enough in statistics is greater than 30, then the distribution of sample means will approximate a normal distribution, and this approximation gets better as n gets larger. But if the original population is itself normally distributed, then the sample sizes can be any size, and the distribution of the sample means will be exactly normally distributed. So let's see if you understand what we've been talking about for the last 10 minutes. Which one would have less variability, a single value or the sample means? Think about this for a minute. Right, the sample means would. Now, the notation for sampling distribution of sample means. We have the mean of the sample means is denoted by a mu of x bar, and we saw a minute ago that the mu of x bar will always be equal to the population mean. And the standard deviation of the sample means is denoted by a sigma of x bar, and that will always be equal to the population standard deviation divided by the square root of the sample size. This is such an important concept that it has a name. This concept here, this idea here, is called the standard error of the mean. So in applying the central limit theorem, remember in section 5.3, when we had to standardize a value, we did value minus mean divided by standard deviation. But when we're standardizing using a mean, the values are sample means, but remember mu of x bar is just equivalent to the population mean, but the standard deviation of the x bar is the population standard deviation divided by the square root of n. Often we just use Minitab. In this class, we're going to almost always just use Minitab and not do all of this stuff by hand. So all you need to do is calculate the standard error of the mean with your calculator, and then use the same procedures as we did in section 5.3 in the last lecture. So let's look at an example. Here's chapter 5, section 5, number 1. Part A says, what is the probability that one man has a weight less than 167 pounds? Well, this is the exact same problem we were doing in the last lecture. We go to calc probability distributions, normal. We select cumulative probability. We enter the mean, which was given in the problem as 172, and the standard deviation of 29. Input constant is 167, and we find that about a little over 43% of all a man has weight less than 167 pounds. Now let's apply the central limit theorem to part B. Now we're taking a sample of 36 men, and we want to find the probability that the average weight of these 36 men is less than 167. We do exactly the same thing we did before, except we have to calculate the standard deviation with our calculator, which is the population standard deviation divided by the square root of the sample size. 29 divided by the square root of 36 is 4.83. So we enter in this new value now as our standard deviation. Everything else stays the same. Our input constant is still 167. And we find the probability that a sample mean of 36 men is less than 167 is a little over 15%. Okay, so that's an application. That's how we use the central limit theorem. We have one last topic to cover in section 5.7. And we want to be able to assess normality. So the first thing we might do is get Minitab to draw a histogram for us and see, does the histogram approximate a bell shape? If it doesn't, then we would reject normality. Or we might look for outliers. Remember in chapter 2 we saw that outliers are things that lie outside of 2 standard deviations. We might do a box plot and look for the asterisks, because Minitab does our box plots with the outliers being denoted by asterisks. If we have too many outliers, then we would again reject normality. But the new concept we're going to see in this section is doing something called graphing a normal quantile plot. Now, the normal quantile plot is we're going to graph these points x and y, where all the x's are the original data set values, and each y is the corresponding z-score for each of the values. Then we'll often do this through technology with Minitab, because you can get Minitab to standardize values. But we're going to look at doing this normal quantile plot by hand. Just to understand how to do it, we're going to actually do them with Minitab. So first thing you do is sort the data from lowest to highest. And then since you have n values, you're going to separate them each by 1/n of the area. Then you're going to use the standard normal table to find the corresponding z-scores for each of those values. Then you're going to match the original data value with its corresponding z-score and plot those points. And you're going to evaluate this plot, this graph, using this criteria. If the points lie close to a straight line, we're going to say it's normally distributed. But if they do not lay close to a straight line, or if they have some kind of systematic pattern, when you read section 5.7, you saw if it makes kind of an S-curve like this, that normally indicates skewed data, then we would say it's not normally distributed. But if the data looks linear, then we're going to say it's likely a normal distribution. The more points you have, the more strict this linear condition must hold. But remember, we just did that so you could understand what a quantile plot is. We're going to let Minitab do all of that work for us. To do that, we enter the data into a column, then we go to graphs, normal probability plot, and we get Minitab to graph a normal probability plot, which is not exactly the normal quantile plot, but it is similar enough. It does the same thing. So then Minitab gives you a graph that has 2 ellipses with a line down the middle, and all the data values are plotted. The closer those data values are to the line, outliers are values that fall outside of those ellipses on either side of the ellipses. And we're looking to see if we see some kind of systematic pattern, like an S-curve happening. That would indicate skewness. You'll see some examples of the normal probability plots in your book in section 5.7. And when you read your Minitab lab manual for the lab that goes with this section, you see it's lab 6. You'll be calculating and doing some normal probability plots and evaluating them. So that is the end of chapter 5.